So last time we actually have talked about the basics of the convolutional neural network. Okay, so let me just try to. So convolutional neural network, the most important uh, concept is to include convolution as one of the operators or one of the most important techniques to try to capture the feature, okay, when you have some input. The input, we are using the example of vision, okay, the image. So, for example, if you have this picture of a cat, okay, we could have many different ways for us to be trying to capture the feature. Because if you are trying to send all these pixels to the machine learning, it's going to be a lot of data, too much information, okay? By using different technologies or techniques to extract the feature, we can try to reduce first the data volume. Second is to only keep the important information, okay, and also actually try to, maybe already recognize many different things from the image. So we have talked about, if you don't use the convolution, you could, for example, simply use some distribution of the features or the RGB colors and such and such. But by using convolution, we will be able to capture the whole image, okay, and not in just a sequential way, but capture the relationship in a spatial uh, neighbors. Okay, so we are taking the whole area, which could be a patch, which could be, you can think of that just as simply, some small area of sub area of the picture. Okay, and we can apply different filters, okay, to try to capture different important information. So the convolution is to go through each of the sub area. If you use the 3x3 filter, then you every time you will be taking 3x3 pixels in the picture, and then will generate one output. Okay, so the 3x3, then we have the idea of the stride is that depending on how many cells or how many pixels you're going to skip. You can be doing every time shift just one position, or you can try to shift two positions or even more. Okay, that will be the stride for us to say, I'm not going to look at every detail repeatedly, but I'm going to look at, say, for example, if I have a 3x3, and if I skip by two, then I would have only one area or 2 pixels or 3 pixels that will be overlap. Okay, so by using the idea of the stride, you could produce less information. The output information will be smaller than if you try to scan each of the neighboring areas or each of this neighboring patch. But when you are trying to do the striding, okay, to have the stride, then sometimes that your original information, which say, for example, you have 32 here, it may not be able to give you enough positions. So therefore, we need to have the padding around the original pixels, okay? And usually we put the zeros around it to say that this is going to be something that there's no information beyond the original picture. Okay, so we put the zeros there. And so when we capture the picture, still you will be able to say only those important information will be kind of processed by the filter. Okay, so here is a very simple example. Suppose you have originally you have 32 by 32 picture. You have 3 channels of the RGB, and we could be using 6 different filters to try to process all the information on this image. Okay, and all these 6 will be processing from the same image, and it will produce some output. Okay, when you have 6 filters, that's what we say you're going to produce 6 different outputs. And we say that your output actually will be 6 channels. Okay, that's the idea of the channel. The channel means that originally you have 3 channels, which is RGB, but whenever you use different filters, okay, each of the filter will produce one output. So therefore, we consider that to be one channel. So each of the filter of the 6, you will be a 5x5 filter, but the 5x5 still will process every channel from the input and then produce just one output pixel. And so therefore, your filter actually will be total of 6 times 3 times 5x5. That will be the total size of filters. Those filters actually is not produced by you or by the designer. Actually, these are the filters. The actual numbers that will be used in the filter should be learned by the machine. So the machine learning actually need to fill in for these 6 filters, what are the numbers they would have, or what we call as the weight, or the actual values of the metrics, okay, for each of these convolution layers, okay. So from the original 32 by 32 by 3, okay, when you after you have done this one layer, which is 6 filters, then you will produce actually each of the 6 will produce 1 by 26 by 1 by 28 by 28. Why 28? Because when we have the 5x5, the 32 actually will be, if you have a stride of 1, then you will be taking output will be, because the first one is the boundary is going to be from 5, and 5 to 32 actually is going to be 28. So therefore, the output is going to be 28 by 28. Okay. But because you have 6 channels, so therefore your output actually will be 6 by 28 by 28. There will be the total amount of information which is going to be in the output. Okay. So this is the output. This is going to be converting from the input, one layer of the convolution, output of this. But for the machine learning, actually, it needs to find out all the numbers in the filters. That's what we're going to be, doing the optimization. We're going to try to produce what actually is going to be in this. Okay. There also will be a bias term, okay, in many of the machine learning. So in addition to the filters, you might also have 6 bias numbers, okay, in each of this, because whenever they are doing convolution, you have this multiply into the filter, okay, and then you will have also the bias term. But the bias term, you can see that when you have 6 channels, it's only 6. Okay, so even though this is part of learning, but in most of the time when we are calculating how many, what is the size of the parameter, we don't really take this into account because in comparison, this is a much smaller number. So therefore, usually we don't count this. Okay, but if you kind of go through this one here, you can see that you'll be doing the convolution, and then you produce all this output. Then after that, usually we will have an activation function here to go through each of the output pixel or output value, and then try to decide what should be sent to the next layer for the input. Okay, and so this activation function, we will talk a little bit about later on. In addition, we also have this pooling. Pooling is simply, again, strictly trying to reduce the amount of information. So when you have a picture like this one here, okay, you can see that when we are saying that this one here is 4x4, there's a total of 16 pixels or 16 values. Then if we take each of the 2x2 and convert them into a single value, then the total information is going to be reduced to 1/4 of the. So you can see that whenever we're doing the machine learning, we're doing the deep learning, because the amount of information from the input could be a lot. Even though your picture itself is only 32 by 32, but because when we're trying to train the network, okay, the network, the original input size could be millions, or sometimes thousands of, hundreds of millions of information. So we try to reduce the information as much as we can without sacrificing the content of the information. So here you can see that from this original the information, okay, this is a 4x4, okay. When we do the pooling, and if we take out of each 4 cells, we take the largest value, then among the information in here, it means that original picture here, what is the most important or what is the largest value will still be kept, even if we do the pooling, downsizing that to something like this. Okay, so if you compare this one here with this one here, from the human eyes point of view, probably the 6 here will be the most important for us to capture. A here will be the most important one for us to capture, and 3 here will be the most important. So all the important values are kept if you do max pooling. But on the other hand, sometimes if you are saying that, oh, I'm not just trying to capture the most important kind of pixel, but I'm just trying to see the global idea, then you can also try to use the average pooling. The average pooling here will be, instead of taking the maximum value, I'll be taking the average of all these values together. So this will be something that we will have the average value from each of the 2x2 areas. Okay, so pooling is also a strategy for us to be able to reduce the information. So in general, when we try to do a deep learning, okay, using the neural network, we will be creating many different layers. Some of the layers, for example, will have the convolution operations. Then some of the layers will be trying to do the activation. Activation is to try to make sure that some of the information, will be kept, but those information not so important, then they will probably will not try to send it to the next layer. Okay, so here is a possible architecture. We'll have a convolution, then we'll have the ReLU, then we have the convolution again, then we have ReLU. Okay, and after that, then we do the pooling. Okay, each of this, you can say that the convolution is reducing the pixel size. Okay, originally we have maybe 30 by 32. Each convolution we reduce it to 28 by 28 and reduce it to smaller and smaller area. But the number of channels that we use in each of the layers, it doesn't need to be 1 or doesn't need to be 2. Sometimes actually we use a lot of the layers. So the amount of information still could be quite a lot. Okay, even after we have done the convolution. So the convolution is to capture the feature. Okay, but the total amount of information may not be reduced so much. On the other hand, whenever we do the pooling, then we'll reduce the information to be much smaller. Okay, reduced by a quarter or even bigger. So we do this multiple times. Okay, and then eventually we hope that the machine learning and all the convolution would have captured all the important features from a picture. Okay, and then we just simply use a fully connected layer here to say, once I recognize there are so many different features that has been captured, the combinations of these features together, can we try to conclude that that particular picture inside here, it should be either a car, it should be a truck, it should be an airplane or something. And so here is the actual decision making here to say, I have captured all these features. I have captured that, this car, this picture here inside, there is a wheel, there will be some light, there will be this and that. What can I say about this feature? Okay, and this is a fully connected layer that we're going to put all the features and then just try to have the real machine learning here to try to understand what's going on. Okay, so from what we have talked about, some of the basic components for the CNN. The most important one is convolution layer. Okay, and then we have the pooling layers, and then we have the fully connected layer. Okay, and all of this will be something that is going to be designed by whoever is building the model. When you define the model, okay, you should say, I want to have this layer, I want to have that layer, and I want to have this and that. Okay, you also should give activation function to decide what kind of information you want to pass along from the output of some convolution layer. Okay, that will be the activation function. Okay, and finally, one of the operation that we might do is what we call as a normalization. Normalization is not to try to reduce the information. Okay, all of this, convolution, pooling, and then activation, they are all trying to reduce the information so that we don't have so much we need to consider. But the normalization, the idea of the normalization is to say that sometimes if your original input is too heavily kind of leaning toward one side, then we can try to make sure that information is more evenly distributed. So for example, suppose we have a picture. And with a picture here, we are taking a picture of a sky. So inside the picture, there will be a lot of very bright information, and there will be a lot of information which is probably just blue and maybe some cloud. Okay, so when you try to capture the features, okay, it's going to be very heavily to say, oh, here, this is a, kind of bright, and this is a little bit not so bright, and this and that. But the whole thing, in any case, is too bright. Okay, they are very heavily on one side. Okay, or if you take a picture of some dark area, then most of the pixels actually would be very dark. Okay, the idea of the normalization is to say, well, can we somehow change the information so that they are more evenly distributed? That is, when this is the, mostly are dark, we brighten the pixels so the pixels can be more clearly seen. There are some, kind of small details between dark and not so dark. Okay, for the sky, maybe bright and not so bright. Okay, so we can use the idea of the normalization here to say, let's try to shift the information so that the values are more evenly distributed. Okay, so the normalization, sometimes that we can do it in many different ways, but sometimes, most of the time, we try to, every time when we train the information, remember that, because the information original input, it could have hundreds of millions, okay, and we usually try to train them, in one batch, a mini batch. Each mini batch could be 32, could be 64, and such. So after each batch, okay, then usually we try to say, okay, I have already computed all the output. Okay, let's try to have this batch of the information to be even distributed. So we will usually apply them to only the output from that particular mini batch. Okay, and we'll be using the formula, something like this one here, which is for every piece of information in the batch, the output of this batch, okay, we do this subtract the mean value from them, and then we divide it by the square root of the variance. Okay, so this is something that we will see that when you have some picture where all of them has a very large value, by subtracting the mean from the value, then you can move everybody kind of more toward the, closer to the average value. Okay, so therefore, some value will be on the bigger side, some of them will be on the smaller side, rather than everybody has a big value. If you everybody to be the small value, and if you subtract everybody by the mean, then you can move everybody to the center. Okay, divided by the variance means that originally they may be very close, but if you take the variance and divide it, then everybody's distance between them is going to become wide. So originally, when you have a cluster data, if you use this normalization, then the information will become to be more widespread. When you have more widespread, then it will be easier for the machine to try to understand the subtle difference, the minor difference between them. Okay, and that will make the machine learning to be much more effective. Okay, so most of the time we can use the batch normalization, which for every batch, okay, then we try to compute first the mean, the variance, and then we make everybody's value xij to be, something which is going to be a new normalized value. Okay, and usually we insert it after each of the fully connected layer. Okay, before we send it to the activation. Okay, so we have fully connected layer, or we can be a convolution layer. Okay, after we have done the convolution layer, then we try to normalize everybody. Then we decide that what information is important for us to continue the process. For those not so important value, which is a very small value, then we simply, just skip that. Okay, so this is usually what we do when we try to do that. Okay. So these are the basic components when we're trying to build a CNN. Okay, you have all these different choices. Okay. So the question now is that how do you actually build a specific neural network? And we have seen this example here that I've shown you that this is a very simple model. And when you build a model here, so for example, this is a CNN, okay, and then you can see that he has defined the first layer, he has defined the second layer, and then he defined what kind of fully connected layer he wants to use. And then we simply say, oh, I'm going to have layer one, I'm going to have layer two, then I'm going to have something, then I'm going to do the fully connected. So this actually defines is a decision as a model designer. You decide how many fully connected you want to have, how many what kind of activation function you want to use. Okay, and you can also decide that how many fully connected you want to have. So if you come back to look at this one here, so this is one specific architecture. It says that I'm going to have 1, 2, 3, 4, 5, 6 convolution layer. And each convolution layer, I have the ReLU and I have the maximum pooling in here. Okay, so I have total 3 maximum pooling. And after that, I have 1 fully connected layer. This is the implementation by this particular model designer. But you could do something quite different. Okay, this one here decided to use only 2 convolution layer and only 1 fully connected layer. So different, they are different. Okay, so in the computer vision research, okay, people actually have tried to try different ones. Okay, and today we're going to look at some of them. Okay, and then try to make some conclusion to see that what are the best strategy for us to be designing different type of convolutional neural network. This is a very quick kind of overview of the well-known architecture that people have designed. Okay, and this is trying to compare them in terms of the result of using different architecture to try to, there is an ImageNet, okay, which is data set that people have been using that as a standard benchmark to compare how useful or how successful each of these different type of architecture can provide. Okay, starting from 2010, okay, at that time that people actually have not really using deep neural network, but they have already started to use the convolution. And at that time, they have very shallow network, such as like the example we have here, we have 2 layers. Okay, so originally we have very shallow network, 1 or 2 layers. Then 2012 is a year that actually has started to make the deep neural network to be very successful or very brought a lot of attention. It's the first time that AlexNet, okay, was proposed and was implemented. And the AlexNet has used 8 different layers, okay? And the following year, 2013, the next version of the network, again, with 8 layers, has been implemented. Then 2014, the people started to say, oh, if you can do much, so good using 8 layers, why don't we make it even deeper? So in 2014, the VGGNet has experimented with 16 layers and 19 layers. And 19 layers, okay, has been shown to be quite successful. Compared with the next year, 2014, 22 layers from Google. So the blue lines here would be the error rate. Okay, so you can see originally error rate was 28, 25. Okay, but when you have a layer, it has dropped to 16. When you have another, it dropped to 11. Okay, then when you increase it to 19 layer, okay, it has dropped to 7.3. Okay, and then in 2015, okay, the ResNet say, well, if increasing the layers actually would make your system to be better, why don't we try to even more? Okay, so in 2015, they have increased the size to 152, very big jump. Okay, and so from here, this is only 19 layers, 22 layers. Then in 2015, it's jumped to 152. Okay, then of course that in 2015, this is ResNet, then people have, kind of stay at 152, but they say, well, layers is not the whole story. When you have more layers, definitely it will be better. But they have tried to say, okay, can we try other different type of techniques? Okay, and they stay at 152, and you can see each year from 2015 to 2016 to 2017. Okay, 152 layers become to be something that is kind of a very dominant. Okay, people have always been using 152 layers. Okay, so from 1 or 2 layer, a layer, okay, already here you can see that the first drop here, okay, makes the deep neural network to be successful. And then increasing that with 19 layers, as we will talk a little bit about today in the VGG, we also increase the layer, not just increase the layer, but also use some of the techniques, okay? And also then from into the ResNet, increase the layer to be quite a lot, but on the other hand, they also have used some other techniques, okay? They have shown that actually layers definitely is very important, okay? But later or after the 2017, it's shown that you don't always need to have so many different layers, okay? This one here, you can see there is no year, but it says human. What does it mean? It means when we don't use the deep neural network, but we actually use human, we give the data, okay, all this ImageNet for human to try to produce an output. Okay, human can actually achieve on average, okay, the error rate is 5%. So which means starting from 2015, already machines, deep neural network actually are doing better than human. Human has beaten us since 2015 with 152 units. Okay. Human, how do we see? We don't know, but that's how we see things, and we can, kind of have about 5% error rate. But machines actually, using the deep neural network, okay, starting from ResNet, is actually, I think, of course, it is no surprise to us now. We, in our current generation, we know that actually AI can be better compared with human in many different ways. But like 2015 at this time, when they achieved this frequency, it actually shocked the whole world. Okay, just like the first time the human chess champion was beaten by AI. Okay, so 2012 is the first time, when we started to use the CNN and we started to use the deep neural network, okay? And the AlexNet, okay, which we'll talk about, in the next few minutes, has this architecture. So it has a first layer is a convolution, and after that, it has a max pooling, reduce the size, and you normalize the output, okay? Then it has a convolution 2, and then the convolution 2 also, after that, we have the pooling, we have the normalization, okay? And then we follow with three different convolution, and then max pooling. After that, then all the learning of the features has been done. So it goes into the fully connected layer. Okay, the fully connected layer, then try to learn from the things. And this is the picture that you usually will see when people draw that, okay, from left to right, okay. The details of this, let me just try to show you one big summary. Okay, so basically this is the architecture. So the input original picture is 227 to 227 by 3. That's the original, each picture size. So you use the convolution, okay, the convolution has a 96 11 by 11 filters, okay, and 11 by 11 filters that will be done not in stride 1, but in stride 4, which means that 11, then next time we will move to, from 1 to 11, next time we will move to 4, right? Stride 4. So next time it will be from 5 to 15. Okay, the next one will be 10 to what? 20. Okay, so that will be the way that is doing the convolution. And it has a total of 96 such filters, okay? Because it's trying to use each different filter to try to capture different type of features, information from the original big picture. Okay, so it has actually 96 different patterns it's trying to catch. Okay, and so it's trying to capture all of this. Okay, and because it's using 11 by 11, okay, from 227 to 27. So if you do the calculation, you can see that it doesn't need to have any pattern. It doesn't need to have an extra 0 bit by the end. Okay, but the output of this, okay, is going to be 55 by 55. How do you come from 27 to 27 to 55 by 55? You just need to do this first. It's going to be 11 by 11 by the stride of 4. So a stride of 4 basically means that it's going to be capturing every 4 pixel into 1 pixel. Okay, so if you divide it 227 here by 4, okay, basically you can have 50 something. Okay, and if you multiply 55 by 4, what should you get? It's going to be 220, right? Okay, and but here it has this it has a stride of 4 and it has this and that. So therefore, the output here, you can do the calculation. It's going to be 55 by 55. Okay. Anyway, so after this, okay, let me skip this first and then we can do this one. Okay, so after this, the next layer is a mixed pooling. And the mixed pooling here is doing 3 by 3. Okay, so from the original 55 by 55, you will be taking 3 by 3. So every 9 pixel, okay, every 9 values will be producing 1. Okay, and it's also trying to do the stride of 2. Okay, so if you do this one here, you will see that the output here actually is going to be stride by 2. Okay, a stride of 2 means that 55 here basically will reduce by 2. Okay, because it's not taking every shift position, it's taking every 2 position. So the 55 here is going to divide by 2. It's going to basically it's going to be 28. And if you do the calculation of 3 by 3 filter, then you see that the output here is going to be 27 by 27. Okay, so from the original picture, 227 by 227 to by 3 down to the normalization here, okay, or the pooling here, it's going to be 27 by 27 by 96. Which one is bigger? So this one here, let's just round it up. Okay, if we do 30 by 30, it's going to be 900, right? If this is not 27, 30 by 30, it's 900. And 96 here, take it 100. So it's going to be 9,000. Roughly 9,000. Okay, but here, okay, if we do 200 by 200, it's going to be what? 200 by 200, 40,000. So by 3, it's going to be 120,000. Okay, so compare this size with this size, we have actually already made a big reduction. Okay, because 40,000 and here we're talking about 9,000 already is one, kind of a 1/5. And then you multiply by 3, so it's reduction of about, almost like 1/20. So reduced from original size to about 5% or 6% in terms of data size. So every convolution is going to be able to reduce data size. On the other hand, because of convolution, actually it has tried to learn about certain patterns in the picture. Okay, and here it's using 96. 96 is quite a lot. Okay, most of the neural network that we don't have 96, but it is trying to capture from the picture 96 basic elements about the picture. Some lines, some darkness, some this and that. Okay, and out of each of these 11 by 11, okay, it's trying to see that whether there is something in there. Okay, so that's the original idea of the AlexNet design. Is to say, let's try to see in this picture here, out of every 11 by 11, is there something special that we should see? Okay, and I don't know whether I have this or not, but in some of the slides, not in here, I'm sorry. But say, for example, like, people are trying to say this is the original picture, okay? And you can imagine that it's trying to capture in each of this. And for things like, kind of landscape or something, it's probably not so important. But when we try to capture this is a dog, so you can imagine out of this, maybe 11 by 11, maybe we will be able to capture the whole what? The eye, the ear, the tail, okay, or the foot, or something. Okay, so from the 11 by 11, if we can capture that, then we can say, out of this picture here, we can see there's one ear, or there are 2 ears, okay, there will be one eye, 2 eyes, the tail, and this and that. So all that information will be captured by each of the convolution layer, okay? So the convolution layer, each of this is going to try to capture that. Then we try to go back to the original here. Okay, so after that, we've done this again, but this time it's using 5 by 5. Okay, so from this, it's already said, oh, there's an eye here, there's an eye here. Okay, and then 5 by 5 and try to see that. How far are they? Okay, or what the combinations of neighboring. Okay, maybe that your picture here doesn't catch the whole head, but it catches part of the head. Okay, then you try to say, oh, this one here has this one here, this one here, and the 5 by 5 here, we try to combine them together. Okay, 5 by 5. But how many filters they use? 256. Okay, so you use a lot of filters. Okay, again, trying to catch different patterns. Okay, so this is going to produce a straight of 1 with a pattern of 2. The pattern of 2 is really, you can do the calculation and see that you need to have extra zeros at the end because that is straight. So this one here will capture to be 13 by 13. Okay, and then after the max Boolean normalization, then after that is simply try to use 3 consecutive convolution, 3 by 3, 3 by 3, 3 by 3, a lot of different filters. Okay, and then each of them is straight of 1, pattern of 1. Finally, it do the max Boolean, producing the output here is going to be 6 by 6. I'm sorry, 3 by 3. Okay, I think this is the input to the max Boolean. Okay, so after max Boolean here, okay, you produce the output. But when you produce the output, actually, it simply put all of them not in a 2-dimensional matrix anymore, but simply sequentialize, make them to be one big layer. Okay, and that particular output here is going to be a total of 4096. So it's going to be 4096, and you can see here it shows this one here to be one is 2048 and the other one 2048. So the two together is actually 4096. Okay, because this is produced by this pooling here. So this 2048, 2048, then you use a fully connected layer, and last fully connected layer to output that to be one of the 1000 classes. So at the end, you'll produce 1000 values. 1000 value, each of them is a score for that particular class. Okay, this particular network here is trying to guess in the picture what is the score for it to be a car, for it to be an airplane, for it to be a flower, to be a pet, the cat, the dog, and this. So there's an output is going to be one of the 1000 class. Okay, so by using this fully connected layer, it tried to learn from all of this. Okay, into using this 3 fully connected layers to predict what's going to be the output. Okay, and that will be our final output is a class score, the score of every single class. How likely this picture here has something to do. Okay, so the idea here is to say that we have an original picture, but we're going to use different convolution here. okay, to reduce the size from the original 227 to 297, eventually to individual features. Okay, but even in the individuals, we still don't know what it is. Then we use the fully connected layer here, and this is what sometimes people say this is a dense layer. That means that every single individual feature which has been detected will be used to try to use this two different linear layer here to try to understand, okay, what kind of particular class, okay, in this picture. So out of 1,000, you will produce a score. The score, it could be any value, okay? And when we compare the output of one to another, we sometimes use the top 5. It means that if this one here is supposed to have just one, particular thing you want to identify, and this one here, you will give a score for any of these classes, and you give a score. If the predicted score, out of the top 5 scores you have produced, if one of them match the label you have for the original picture, then you're supposed to say, yes, this is the correct guess. Okay, because that we don't, your score here will not be just a 0 and 1. You will be just individual score. And if you say this one here is supposed to be a dog, and your dog actually has a score which is highest than you want. But even your score for the dog is not the highest, but it's among the top 5 of the 1,000 value, still you're considered to say, yeah, you have made the right guess. Okay, so you could be comparing something. If you compare the score, you can see that we're comparing score, say top 5 or top 1. Top 1 means that your correct answer should be the top value, but top 5 just means that if you have one of the value of the top 5 is the correct output, a correct label, then you won. Okay, so that would be the kind of the basic idea of the AlexNet. And you can see that AlexNet actually it has some of the first time we use a ReLU here in the activation. It used many different this is not used anymore, but we'll talk about it. And it has a lot of these things which we will talk about details in terms of dropout, in terms of the learning rate and such and such. Okay, so let's take a short break and then we'll continue after this. Okay, let's continue the discussion. Okay, so this is AlexNet. Okay, so AlexNet is the first successful neural network that with deep learning with convolution. Okay, and after that, you can see that people say, well, if you can do it in 8 layers, maybe you can do it with more layers. And so therefore, in the VGGNet in 2014, they started to create even deeper networks. And deeper networks, you can see that it has 19 layers. And this is comparison between the 8 layers with the original AlexNet with the VGG, which can have different versions. It has different versions, 16 layers and 19 layers, okay? And so the two things about difference, one is that, of course, it's steeper. One is 16 layer, 19 layers, and to compare with 8 layers. The second thing is that in the VGGNet, instead of using the big convolution, which is 11 by 11, they have decided to use all of the convolution to be 3 by 3. So you can see that each of this is 3 by 3, 3 by 3, 3 by 3. And it still has the pooling, and you still have the fully connected layer. Everything else is the same. But as we have introduced before, by using 3 by 3, okay, it is able to, if you have deeper, actually, the amount of information you can capture from the original image is still going to be the same, okay? Because when you have 3 by 3, 3 by 3, 3 by 3, then already you can cover a big area. Okay, so they don't need to have so many different layers. So when you have smaller layer, smaller filters, you have a deeper network, then it's going to be okay. So this is the things that it's trying to capture to say that one piece of information in the deeper network, then you can still have cover the whole big area in the original input. Okay, so that makes when you have deeper, it doesn't need to be big filters. Okay, you can have smaller filters. So if you look at the total number of layers, and when they use the smaller filters, okay, then they have done the computation. Then you can see that because you have the 3x3 parameters, okay, the total size of parameters actually is not going to be so big compared with if you have used 11 by 11, okay, which is going to be a lot of parameters, a lot of ways that you need to train, okay. In terms of at the end, when you have fully connected layer, the fully connected layer actually is going to be the same, okay, because they are all from 1496 to 1496 to 1000. So therefore, the fully connected layer, the complexity is not so different. Okay, so the total memory, okay, in terms of this, okay, that you have to store because you have to store the original picture into each individual smaller the intermediate metrics. Okay, it's going to be about 96 megabytes of the per image. Okay, but in terms of the whole number of parameters that you have to store because of this deep network, it's going to be 138 parameters. Okay, so in terms of the total number of parameters, okay, the size of the parameters actually is bigger than the image itself. So the input image that you're trying to process originally is only 224 by 224, but because you have so many layers, you have to store each individual layer's output. Why do we have to do that? Why do we have to store all the intermediate images in the middle? Because we need to do the backpropagation. So whenever you need to do the backpropagation, okay, you need to have the individual values so that you can do the individual, find out the individual gradient. Okay, that is why that whenever we're doing the training, okay, you need to do the training to say, yes, I am going to do the training. So therefore, you'll be saving all individual pictures in the middle of the convolution so that you will be able to do the backpropagation. But when you do the inference, after you have trained the model, all the parameters will be stored. And then when you try to just simply do the inference, you just send the picture over to all the network. You don't need to save all the intermediate pictures. You just need to go through this the deep network. Then you'll be able to produce the prediction directly. Okay, but whenever you are trying to do the training, okay, you need to save all of these individual pictures in the middle. Okay. Okay. So with this, okay, you can see that the VGGNet is quite successful and is able to reduce the error rate to be 6.7. Later on, we have the next network, which is ResNet, okay, and the ResNet is using even deeper network, okay, but the deeper network, in addition to just deep, you also introduce the idea of the residual block. Okay, you can see that in this figure here that is taking the input, then you do the initial in convolution, and after that, use the 3x3, 3x3, but you have this extra line here to say that whenever you have the input, okay, the input going into the convolutional layer, you will go through the convolution operations, but you also will feed the original input directly into the output and combine them together. Okay, so what's the idea? The idea here is that whenever I have an input picture, I will try to use my convolution to try to learn about the features of something, okay? But because there's a ReLU, because there's something in here in the convolution, so the convolution actually may tell the output to say, well, in this convolution, I'm trying to find an I, okay, but I cannot find an I. If I cannot find an I, what will be in my output? Nothing. You will say, I cannot find any specific pattern which is of interest. I cannot see anything which is, your convolution asked me to find. Okay, so, but when we have these layers, each of the convolution is supposed to try to identify something. And if some earlier one says that I cannot find it, and then you tell the next layer to say, I don't see anything, then all the other layers afterward will say, well, I have no information. I cannot see an eye, I cannot see an ear. Okay, and if your later convolution maybe say that I want to find a body, but here says I don't see an eye, zero eye. I don't see a tail, zero tail. I don't see an ear, zero ear. Then the later ones wouldn't be able to see anything. Okay, so rather than just let the convolution to filter out all the information using ReLU, it says that, well, tell me what you see, but still give me the original picture, because the original picture may still have something that later layers want to be able to learn, right? So by using each of the layer to learn something, you also skip it to say, well, take the original picture and maybe later layers can learn something. And so your output here will be the original picture as well as whatever you have learned in this layer. And the two together will be fed into the next one and the next one so that you may be able to learn something. So by using a combination of what you have learned and what you don't see, okay, but let the next layer to say, oh, make a decision whether you have seen something. In addition to this, maybe you can see something, okay? This residual connections allow all the layers to be able to use the information in the original picture, okay? So this one here, the strategy actually proved to be quite useful, okay? And so this one here to say that if your original convolution here produce zero, rather than just pass it zero, you will be able to say, okay, I am going to try to say you have zero, but original picture may still have something. So therefore the two will be added together in order for you to produce the output. Okay, so the residual network is something which is proven to be quite useful because that later layers can see something that you may not be able to see. Okay, just for interest, let me show you this picture. You see anything? 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 Anything yet? Anything? Okay, now you've seen it, right? Okay, so different layers actually detect different things. Okay, so coming back to this original picture. So now, I'm sorry. So now you have seen it, and if I show you the original picture, do you see it? You see it? I have already told you there's a hint, right? There's a deer, right? Can you now see a deer? So if you use the convolution, okay, one of the layers of convolution will be able to catch this. Okay, but for you to make a decision whether this is a deer or not, sometimes just seeing this may not be good enough. you still want to be able to see that, okay, I know that most of you probably have seen the head, right? With the ear and the head, but there is also a body. Okay, so with the convolution to detect also the body, make the decision to say this is actually the deer much stronger than if you just see part of it. Okay, so when you have a convolution neural network, okay, it's actually each of the filter is trying to detect something. Then together, hopefully that you'll be able to, in the fully connected layer, to decide what exactly is in the output. Okay, and so therefore, if I have seen something like this one here, can you see a deer? No, right? So therefore, that particular output will be 0. But if I move to here, is there a deer? Yes, there's a deer. Okay, so by passing the picture to the later layers, maybe if this layer doesn't see anything, some other layers will see something. So the residual network will be able to help you to try to not to miss information just because this individual convolution is not, doing something good. Okay, so by using the ResNet, okay, we can design such idea of the network, and there are different variants of the resolution ResNet. You can have 18 layers, 34 layers, 50 layers, 102 or 152. Okay, and each of them can have different performance. Okay, and you can decide that what do you want to have. Okay, you can have decide how many different layers. Okay, and so basically the different type of network, the AlexNet, the VGG, ResNet. Okay, each of them contributed something. AlexNet show you that you can use CNN to train the computer vision. VGG shows that bigger layer when you have more layers. How many layers are VGG? VGG. 16, 17, 19, 18, 19. Okay, that's roughly that's the layers. ResNet, how many layers? This is the kind of question I will ask you. Okay, you don't need to give a specific answer, okay, but you need to know, roughly. Okay, so if I look at this one here again, roughly, okay, from 8 layers to about 20, 17, 19 layers, okay, then in ResNet jump to 150 layers. Okay, so it's a, kind of order of magnitude, 10 times as much. From the original 8 layers, here is like 3 times, okay, and then we jump to 152, okay. But number of layers is not always important, but definitely that there's a big jump in there, okay. ResNet are good, ones that people have found that actually is quite powerful, and so therefore that it has been the ones that has won the competition, and it has been there for about 8 years, more than 8 years, and people are still using them for their architecture. Okay. Okay. So the basic idea of the CNN is to use the convolution and use many different layers, and assuming you have a lot of input data in order for you to train. Okay, but sometimes in some applications, okay, you may not have so many input data to train, and that is when the transfer learning is becoming useful. Okay, so when you train with the CNN, okay, you run through many of this, you use mini batch, okay, and then you try to say, here, this is the picture I was trying to find. Okay, AlexNet in the first layer is using the 11 by 11, and it takes all of these specific patterns in the first layer. Okay, each of them probably doesn't make too much sense. Okay, but when you put it together with the pattern which detected in the later layers, then you would find that it has something more. Okay, and but at the end, when you have all the features together, okay, then you will be able to use a fully connected layer to be able to train this to see that how many such features you have seen and what are the combinations of them, and then to make a decision what's your output. Okay, but you need to have a lot of information in order for you to be able to detect all these individual features, train the weights so that individual features can be detected correctly. Okay. However, sometimes that you may not have so much data. If you have some small data set, and you try to go through this one here, then you won't be able to have a good result. Okay. So one of the idea here is to say that we know that all this previously in the convolution here, they are trying to detect certain features. And those features, some of them are not so meaningful, but they maybe are used to detect certain basic patterns, okay, in the image, and then use the combination of the image to try to decide what is exactly the output, okay? So if you have all these lower layers, which are able to decide the basic patterns, and you have trained them well, then you don't really need some extra data set to be able to identify those simple patterns, okay? But you need to decide to say that, oh, okay, so suppose that the picture I've just shown you, this is a picture here. Okay, you can imagine that how many, oh, by the way, this picture, I took it myself. I have the copyright. So this is actually what I've seen when I went to one of the parks in not in California, but in Colorado. Okay, so if you look at this picture here, suppose you want to be able to see from this, okay, you can see that there could be many different kind of features you can train from this picture. Some of them are about animals. Some of them could be about the bushes, about the tree, the leaves. Okay, so from a lot of such pictures about landscape, maybe you already have the convolutional network, okay, the convolutional layers that can already decide individual ones. So now suppose I want to train, okay, a system to be able to identify different what you call it, different type of orchid flower. Okay, I don't really need to retrain my network to be able to identify all the leaves. Okay, maybe that in my picture already it has some patterns you can detect about the flowers, individual color, bud, and this and that. But when I have different orchid flower, I want to be able to identify. I just need to have fully connected layer here to tell it to say, well, with a combination of this color, with a combination of this particular pattern inside of the flower, then we should call this to be some kind of orchid. Or maybe we should call this to be some kind of sunflower. So if you look at comparing between the sunflower and orchid, if you have a convolution network already been trained to look at different type of flower, but you have not been trained to look at this specific kind, then all we need to have is to say, well, let me try to give you the correct output. And then from this one here, and from all the features you have detected, I'm going to tell you that when you have a combination of this and this and this and this and this color, then you should be called not the sunflower, but it should be called something else. So if I can reuse or freeze this convolutional network, then maybe I don't need to have so many data in order for me to train the whole thing. Okay, I just need to retrain this part. Okay, maybe the last layer, maybe the last fewer layers, okay? And when you use depending on how much data you have, you can try to train only the last few layers to make the decision without rechanging, detecting the features. Or if you have something more, then of course that you can try to detect some features in your specific data set. Okay, so say for example, suppose that we want to study certain medical disease, which only very kind of popular, say either around the world. Okay, originally maybe we had a data set which only from the Western countries. Okay, so the Western country, they will be looking at a lot of these individual medical images and this and that. They train it, perfectly to detect that particular disease among the white people, among the Hispanics. Now we're trying to detect to say, I have a small data set, and this is going to be for the cases which is in Taiwan. Okay, and so my data set would be not so big compared with the data set which originally from the United States. Okay, so if I use the data set just from Taiwan to try to train it, okay, it may not be able to do a good job because all the features that need to be trained. Okay, I don't have enough number of pictures to train them. But if I use the pictures, okay, or the original image data set trained from the white people, from Hispanic, from all the Western countries, then I just come to use some of this small data set from Taiwanese people. And maybe Taiwanese people, when they have that particular disease, they have some special pattern. Then I just need to tell this fully connected here to say that I know that you have already seen this and seen this and this, but you don't need to worry about all the other details. All the other detail has already been detected. So maybe you can just use some later layer here to say, okay, identify the specific ones, okay? And then you can train this fully connected here to make the final decision to say, this is that particular disease, okay? So that's the idea behind the transfer learning. And transfer learning is especially important for many applications that it doesn't have a lot of data set, and especially, for example, in the medical area, okay, and especially like if you're trying to identify some kind of small data set things like you're trying to say, for example, specific animal species, okay, from time to time that, on Earth we'll discover there's a new species, okay, maybe some new kind of fish from the deep ocean, maybe some special kind of bird from some regional area, then what you need to do is not to try to train the individual data, okay, individual feature, but simply to say, oh, this one here, compared with other fish or other bird, they have something special, okay? And so if you can train a few layers here to identify that specific feature, then you can use that to tell the fully connected here and say, if this particular feature has appeared, and if it has appeared, then you can make a decision that belong to that new species or that belong to that new kind of bird. Okay, so in general, when you have a little bit of data yourself, but if you can find some original data set, they are quite similar, then you can try to use the linear classifier just due to transfer learning on the top layer to say that, okay, most of the features are the same, but the combination of them, okay, are different. So therefore, your simple data set, your small data set will be good enough, okay? But if you have quite a lot of data, then you can try to fine tune more layers, okay, to try to identify more features, okay? But if you don't have, you have very little data, okay, but you have only kind of a different data set, okay, then your original data set may not be able to identify some of the important features in that. And if that's the case, you're going to be in trouble, okay? So you have to try to use different, data set, or try to use different type of combinations of the things in order for you to find out what's the result. Okay, if you have quite a lot of data, then you can fine tune a large number of layers to start from scratch. Okay, so basically, the convolutional neural network is an area that has people have done a lot of study. Okay, there are many different type of architectures that has been produced, and not. I mean, each of them, here is trying to show that in terms of the complexity, in terms of the top one accuracy report, then you can see that each of them they have different area in this space. Some of them has a low operation, but they are able to achieve pretty good result. Some of them they have very high operation, but their result is not so good. VGG in general, okay, has a high operation. Okay, number of operation is pretty big. ResNet in general, okay, depending on how many layers you want to have, 152 definitely has a pretty high operation. Okay, 101 is here, 50 is here, 34 is here, but you can see that the improvement from 50 layers to 101 layer and 152 layers, there's an improvement, but not so big. Okay, and so therefore ResNet here, you can see that it's actually quite popular because it's able to achieve not so many operations, but actually able to have pretty good result. Okay, you can see that AlexNet, okay, is low in terms of the operation, okay, but in terms of the result, it's also not so good. But since this is the first version of the CNN, and so therefore that a lot of people are still using them for teaching, for comparison, okay, but most of the network right now, they are, the ResNet is actually considered to be quite good. There are some of the newer versions of the ResNet plus the Inception, okay, which we will not talk about, but you can see that VGG actually has the most parameter, most operations, but the result is comparable to the AlexNet is not so good, but ResNet in general is something that a lot of people, prefer to use that. You can use the 101, you can use the 50. The result, the improvement is there, but it's not really that significant. So you can use 101 or you can use 50, depending on whether you want to have some extra, kind of manpower that you want to use. Okay. Okay. So let me continue with this kind of some additional things that we should talk about CNN. Okay, so again, just a very quick review that the CNN has a convolution layer from the original picture uses CNN that you produce to have some intermediate result. Okay, and this in this we have the input layer, we have the output layer, and in the middle we have the hidden layers. Okay, in each of the hidden layer, you can, depending on how many layers you want to have. Okay, you can have, more or less depending on what kind of complexity you want to have. We are using the pooling to reduce the size, and most of the time we use mixed pooling to keep the most important features. And we have also the activation, we have the normalization, okay? And depending on, how many layers you want to have, okay, you can have different type of operations and different layers and also different type of residual or not to make the architecture be more powerful. Okay. Activation function. Okay. We have talked about activation function, and most of the time we use ReLU. Okay. But originally, when people started to use the activation, sigmoid was the one that used quite often. Sigmoid, however, has a problem that because the sigmoid convert the input into 0 or 1, okay? And so therefore for sigmoid, when you're trying to do the gradient, okay, when your input is in this range, the output is always going to be 1, okay? So when you are in this range here, you cannot find any way for you to be making changes, okay, to the input in order for you to have different output, okay? Because your input, you can see that whether it's going to be 7 or 8 or 9 or something, it's not going to make any difference. So therefore, when your output is only always 1, you don't know how to decide what kind of weight you should have, okay? Which means that your output, okay, which is going to have saturated neuron, which doesn't have any gradient. When you have no gradient, then you really cannot try to make any optimization in order for you to adjust the weight. The same thing with tangent. Tangent is changing the output to 1 or -1. Again, okay, you have 0 gradient here and here, so therefore it's not so good. In comparison, ReLU. ReLU here, you can see the output and input, okay, when you're in the positive, they are going to be linear. So therefore, whenever your output here says that I need to change the output from something to something, then you can change the weight from something to something to reflect your desirable output, okay? So therefore, ReLU actually is a better activation to use when you have a positive range. When you have negative range, it still would change the output. You know, you always produce the output to be 0. So therefore, here again, we have the problem with 0 gradient. And so therefore, you know, when you have the negative value, you still have the dead activation. And so another version of the ReLU is called leaky ReLU. The leaky ReLU is not to make all of them to be 0, but when your value is negative, then change them to be very small value of x. So therefore, they are not totally flat. If they're not totally flat, then whenever you want to do the optimization, you can still adjust the weight to change the output a little bit, okay? And another, you know, variation is the called JLU. Okay, this JLU here is to make the corner not to be, you know, exactly like, you know, a very angle here, but make it to be a curve so that you can have a continuous optimization. Okay. Most of the time, however, we use ReLU, and ReLU is probably good enough because when you have negative value, it means that, you know, they are not contributing to the optimization, so therefore we don't really care. Okay, but the idea here is that don't ever use sigmoid or tangent. Okay. Okay. Another regularization we have also said is that we can create a regularization factor in your loss function. Okay, and most common ones to use is try to calculate the size of the W. Okay, your weight to make the size here to be a factor, so that we can use the smaller weights. We usually want to have smaller weights in your optimization. Another important strategy is to use dropout. Okay, I think many of you probably have used the dropout. Okay, let me just show this. Not in this example, but in many of the examples, they use the dropout. Okay, basically the idea of the dropout is that if we have some network which have a lot of nodes, okay, when we try to optimize, a lot of time it's going to be taking a lot of effort to try to optimize every individual weight, okay? And also, there is a very common behavior is that when you have the weights, okay, the system will most likely will be tuned, will be optimized, and you have some overfit, okay? And so we sometimes in our training, we on purpose try to kind of simply say, I know that certain part of the neuron is already built into the network, but in the training, we simply to say, please don't use this neuron for you to be producing the output. Okay, by randomly choosing some neurons to be skipped, okay, to be not used, okay, we're going to have some simpler network. But the simpler network also will make the network to try to learn as much as possible by themselves to be able to create a good result, okay? And dropout original, when you look at this one here, you can see that it is kind of a little bit strange. I have already deployed so many people to help me to do some work. Yet, when I'm trying to train the system, I tell some people to say, please take a leave. Don't come to work. Okay? Just stay home. Okay? I don't want you to come to work today. Okay? So the basic idea here is that I don't know whether you do this or not, but in some I don't know how many of you doing the body training, fitness. You do go to gym to work out. From time to time, when you go to the gym, and they would say, "Okay, try do something," and then later your trainer would say, let's try to do a little bit more. Let's make your muscle work harder. Okay, you know the idea, right? So they actually try to say, well, I need to do the stress test. Okay, and sometimes they try to on purposely give you more than you can take. Okay, that will make your muscle to work harder. Normally, you don't need to have that. But by making your muscle work harder, okay, that actually is good for you. Okay, so dropout, you can think of the idea also is that if I use the whole new set of neurons, I will be able to have good results. But by reducing some of the neurons, I make my network to be simpler, but they try to using the simpler network to do as much as the whole network. And so therefore, this would actually make your system to be more capable, okay? Especially, this is the most important reason, especially if your input, the training data set is going to be quite different from your test data set, okay? Because the test data set is usually something you have not seen in your training data set, okay? So by making each of these neurons here to be overloading, okay, just like you would be trained with your body to be able to do more than your original design. Okay, then when you have some new data set, then it will be able to handle more. Okay, this is a very, my mental discussion about the dropout. It's not, mathematical, but it is something that usually in many of the system, we try to make the system to be over spec, to have the over spec, meaning that you try to design system to be higher than it is supposed to be able to do in a normal sense. Okay, so because the trained data set is different from the test data set, so if you train your network to be not always just following the trained data set, you may be able to see something that you have not seen before. Okay, and that make your system to be actually better. Okay, so here that it's kind of an idea that how can this be a possibly good idea when you have a system originally that you try to train the system, it's able to tell whether it has an ear or not, it has a tail or not, it has furry or not, it has curl or not, it has this and that. and you can make a decision after all of this to say that whether it's a cat or not, okay? But by taking away some of this, okay, you simply say, well, as long as it has a tail and it has a claw, then it will be a cat. Then you have taken away some features which the ear is considered to be a requirement. If you don't do this, then your system will, depending on the tail and ear and the claw and furry together to say, oh, this is a cat. But most of the time, if you have claw and you have tail, because claw itself is a very important feature. Okay, if you have a claw and with the additional information, it has a tail, already we can roughly say this is a cat. Okay, then when you have a new picture, and that picture actually, you don't have the whole picture of a cat, but you have certain part of the cat, and it can show a claw, and it can show a tail, then your network should report to say, I think it's a cat. Okay, then it will be better to have such a network comparing with a network which say, I need to have a claw, I need to have a ear, I need to have a tail, I need to have a furry in order for me to conclude this is a cat. Okay, so by using dropout, you on purpose to take away some of the features, but relying on those incomplete features to make a decision that make your network to be, make your system to be more versatile, not better, but more versatile, or in a technical term is more general, not so specific to all the pictures that you have seen, but to some future pictures that have only part of the features. So by training your network to use only part of the features, you make your system to be more general. And in many of the future data sets, maybe they will give you better result. Okay, so that's the idea of the dropout. Okay, another idea of the dropout is to say that you are kind of removing some of this. So you are, instead of creating one network, okay, or one CNN, okay, you can be thinking of you are creating combinations of such different type of networks. Some of them are missing some of these features. Some of them are missing some other kind of features. So you randomly choose some features to drop. It makes your network to be able to have different combinations of the capabilities. Okay, and again, coming to this is that your network may decide to say that a claw and tail is good enough to say a cat, and maybe a claw and some furry can also make a cat, and a claw and it has ear which is like a dog, cat ear, then we can say it's a cat. But you don't need to have all of them for you to decide this is a cat. You just need to have part of them. Again, you have different combinations of them together to be made a cat. So dropout actually will produce not one network, but actually train a large ensemble of different models, okay? And each of them will give you some idea about the possibility of this is a cat, okay? And so therefore the dropout is a strategy used quite often in producing some networks, okay? So you can see that this is an example that when you have something, you may multiply with some p here, and p is the probability to say that whether I want to have all of them or I want to have just part of them. Okay, and you can use a combination of that in order for you to drop in the training time. But when you do the testing, you want the whole network to be working together for you to make decision. Okay, because each of the features that have been trained, still they should report to say that whether they have receive something or not. Okay, yet another way for us to be making our system to be trained better is sometimes that, again, if we have small data set, and if your small data set here doesn't have enough data, then we quite often will use data augmentation. And data augmentation allow us, we try to use strategy to say that here I have a picture of a cat, okay, but instead of just one picture, if I flip that, okay, or if I rotate it, okay, or if I try to take part of this picture here, then I can increase my total data size. And each of data here I reuse, okay, so if when you flip them, you can see that they will be detecting features a little bit different. Here and this one here, they are different, okay, but they are from the same cat, from the same picture. So we know that from the logical point of view, when you flip them, you are not changing the fact, you are changing the shape, but the idea, the knowledge, or the intelligence, this should also be identified as a year, will be, will be learned by your network. So if your original data set is not so big, then you may want to use different strategy of data augmentation. Flipping is one of them, taking a subset is another one of them, okay? And you could also be, doing cutout. So cutout is very useful, especially if you, say, for example, a cat, okay? A cat could be hiding behind certain things. But in the original picture, you only have a cat. But if you do this and you make the system to learn to say, oh, this one here, you should still report this to be a cat. Okay, that will make this one picture now have 5 different possible ways to be identified to be a cat. Okay, so using all these different strategies, okay, data augmentation using cutout, using randomly, kind of choosing part of them. All these are ways for you to be still training the same network, but you are using different input data or different ways of doing this and that so that your system can be better for testing data. And the testing data could be something that is not seen in the original. Okay, learning rate. Learning rate is the strategy for us to say that whenever we are trying to, make the optimization, okay, usually our optimization will try to define the loss function, and the loss function here, let me see whether it has a definition. In this one here, okay, let me see where is okay, so this loss is simply defined to be parameter passed, okay, for the optimizer. But in general, when we try to decide that how much we should update the weight, okay, the learning rate is a strategy for us to be deciding that how much change we should make to the weight, okay, according to the loss function, okay, and sometimes we try to use a smaller or larger weight loss rates so that we'll be able to make the loss to go down. Okay, so the loss rate is something that usually we try to make the loss to be initially is bigger, but later it's smaller. Let me see if I have. Okay, it doesn't have this in here. Okay, but loss rate is part of the hyperparameters that we use to do our training. Okay, in this simple example, I thought I have other examples, but in this one here, simply use some of the simple loss rate, how many epoch that you do the training and what is the batch size, but there are other different hyperparameters you can choose to do. Okay, but here it's trying to say is that whenever you're doing the training, you should look at the loss from the training and from the validation. Okay, if both are going up, okay, then it means that you can continue to train. Okay, but if you have a training, you find that when you're doing the training, the loss is getting, the accuracy is getting better and better. But when you do the validation, your training, your validation start to go down. It means that you probably need to, to increase your localization, or you can, some data, because you are trying to make your system to be too much, kind of targeted towards the training data set. This is what we call as the overfit. Okay, so therefore that whenever you see that your training accuracy is getting better, but your validation actually is getting worse, it means that you need to change your hyperparameter, change some strategy. Okay, but if you have both your training and validation, okay, kind of following the same route, okay, there's no gap in between. Okay, it means that you need to train longer, but also probably that your model is too simple. Okay, you probably should try to make your model to be more complicated, to have more layers, to have other different things. Okay, so that you will be able to have a better result. Okay. Okay. So in general, when you try to train the system, okay, you pick some initial loss function. You just try to use a small subset of a sample, okay, and then try to do as much as you can, okay, and then also try to find, okay, the learning rate, okay, to see that whether you can adjust the learning rate and you see that your loss actually will go down, okay, and then you try to change your grid, okay, to make your convolution in your convolution here to have a coarser grid, okay, and you train it to see how you good, how it behave, okay, and if it's kind of good, then you try to refine the grid and then make it to train a little bit longer, okay, and finally you also try to look at this this curve between the loss and the accuracy to see that whether you can your training output and your accuracy output, whether they are both are going in the right direction or not. Okay, you want to have something like this one here, then you can you want to continue to train longer. But if you see something like this, then you need to change your model. Okay, and then if you have something in this one here, again, you want to probably that your model is too simple. You want to either train longer, and also that you want to make your system, your model to be a little bit longer. Okay. Okay. So basically, that's all I want to talk about CNN. So the job of the CNN we have discussed so far is about try to classify when you have a picture, okay, to say this is a cat, this is a dog, this is something, okay, and to give the scores or try to produce the probability what it is, okay. But in terms of the computer vision, in addition to the classification, there will be some other type of computer vision task, okay? Classification is simply to say, the picture, this is a cat. But once we know there's a cat in the picture, what we usually would like to do is to say, in many of the systems, can you show me the area of the cat? Okay, because we know that in many of these newer AI capability for generative, we want to be able to replace the cat with something else. Or maybe that once we identify the cat, we want to move the cat to some other picture. Okay, so we need to be able to know specifically what are the boundaries, okay, what is the specific areas that a cat existed in this picture. And this is called the semantic segmentation. So semantic segmentation is take a picture and then produce the output, okay, and that output is going to be able to say, oh, here is going to be the sky, here is an area with a lot of trees, and here is a cat, and here is the grass. Or maybe that in some cases, you don't really care about the rest of them. You can label the rest of them to be background. In the foreground, what is the cat? Okay, so that is a task what we call the semantic segmentation. Okay, which is different from another segmentation called instance segmentation. So what is the instance segmentation? Instance segmentation means that I know there is a cat, but maybe there's more than one cat in the picture. Then I want to be able to, for each cat in the picture, they should be kind of identified with a different shape area. So in this picture here, you can see we have 2 dogs and 1 cat. Then you're able to say, there's a dog, there's another dog, and there is a cat. Okay, so the segmentation, semantic segmentation, if you're using semantic segmentation in this, then you will show that both of these 2 are dogs, but it doesn't try to identify each individual dog. Okay, but instance segmentation is different. Instance segmentation says that I want to be able to show each dog in its own shape. Okay, and so instance segmentation is different from this because in addition to just show the area, you just classify, you also need to be able to do the object detection. What is object detection? Object detection means that in this picture here, we can see there's 1 dog, there's another dog, and there's another cat. For all the things inside of the picture, you would show the what we call as the bounding box. In this picture, which area has a cat, which area has a dog, okay? So you should show the bounding box, but also the object, okay, or the class of the object that is in this bounding box, okay? So the object detection here should be able to show the boundary and show the boundary here, not in terms of the segmentation boundary, but in terms of the bounding box, but also identify that to be one instance of that particular object. Okay, so classification, segmentation. Segmentation is semantic segmentation and instance segmentation. Okay, and object detection. They are all different tasks. Okay, different things that we can do to use the convolutional network to be able to identify to show the output. Okay. Let's just continue and we can finish earlier. Okay, because I think it's okay. I'm not going to go into a lot of detail. I just want to show you the basic, kind of the general idea. Okay, because after all that, this is not the course about specific about computer vision, but I just want to show you. But the idea of the convolutional neural network is important because all of them actually are still using the same idea. Okay, using the same way, but just define the things a little bit differently. Okay, so the semantic segmentation basically is trying to say that inside of a picture, okay, I want to be able to tell, okay, in the original classification, for the whole picture, I just want one output to say, this is a cat, okay? It doesn't tell me what are in the backgrounds, okay? But in the semantic segmentation, basically the idea here is to change it so that I can tell every individual pixel of the picture, okay, I need to say that what it is about, okay? So here, if I point to this one here, if I point to this, it should be able to tell me, say, this pixel here belongs to a cow. If I point to this one here, you should say, this pixel here belongs to a sky. Okay, so the original picture, the classification is to say, this whole big picture is about a cat. But now the question is that, what about this pixel? Just one specific pixel. What is it about? Okay. And to answer that question, definitely, it's not going to be so easy. Because if you look at this whole area here, if you take one pixel or one area, it's all black. So how can you learn to say, oh, this is a car? Impossible, right? So we need to have what? Whenever we want to say this is something, we really need to look at not just that particular pixel, but that general area. Okay, and to see that, oh, okay, this particular one's actually is part of a car. So therefore, this particular pixel, I should say, is a car. Okay, so it's going to be something that we are trying to report individual pixels cars. But instead of doing that, we should say that this pixel is in something, which we can say is the sliding window. We go through the picture and say, oh, this area here has something, and so therefore this picture belongs to this area has something, this is going to be something. And in other words, okay, we are trying to identify not just individual pixel, but identify patch. Then when your pixel is in that patch, and that patch is identified to be a car, then we said that particular pixel is a car. Okay, so what are we saying? What we need to do is that for every pixel, I need to look at the patch. Then from the patch, can I use the same idea of our original CNN of a picture to look at this as a stock picture, okay, or a part of a picture, or a small picture, and can I identify this picture here is some particular class? Okay, so instead of looking a whole picture and then output this as a car, I'm now going to take one spatial area, and one spatial area identify what it is. Then when I identify what that is, then I report that that pixel in the center of that is a car. Okay, so it's like something that I'm going to try to do it, okay, by dividing an original picture into individual patch. Each patch would help me identify the center of the patch, what class it is. Okay, so using this idea, you can see that, okay, if I just simply straightforward do it this way, then it's going to be a lot of work, okay? Because every pixel, I need to take a patch. Every pixel, I need to do a patch, okay? And then every patch, I need to output what it is. And then I use that to say, oh, that particular pixel is something, okay? So if I can do that, then for every pixel, then I simply say, oh, if this is a car, I will show in this color. Then I will be able to convert this because every pixel I have I have an answer to say is a car, or is it sky, or is it tree, or is it grass. Then I will be able to show different color from the original picture into this color, and these colors here give me the segmentation of the whole thing. Okay, so I can try to do this, okay, or I can try to identify the whole thing, okay, by not dividing into individual pictures, individual sub-pictures. I can take the whole thing and then do the convolution, not just always keep the whole thing. And in order for me to say, oh, okay, I'm going to try to understand that for every particular pixel, what's the output, okay? But probably the better way is to try to take the whole picture, okay, and then try to understand, okay, try to use a convolution to capture certain features in order for us to understand what are the features in the picture. Okay. Once I have that, then somehow I can, because I have already identified the features, I identified there's a cow in there, then I can simply upsample, okay, which is to say that from the features, I know that there's a cow in there, okay, but in the middle here, okay, I really am not really looking at the original picture, but I'm looking at only the features. But that I can try to expand from that back into the whole picture, okay? And if I can do that, then I will be able to, in one shot, okay, to do this and then to try to look at the whole picture, okay? Because I already know that there's a cow. Okay, there's a cow, or there are actually two cows here. Then I can try to say, okay, I know the cow, so let me try to identify the position of the cow in the picture, and then I can just tell them each of the pixel here, you belong to a cow. Okay, so so the idea here is that I know that how we can do the convolution from the big picture into the smaller feature. But now I want to be able to say, once I have identified the feature, how can I make it back to be the big picture? Okay, and this is what calls the upsampling. Upsampling is to say that I already have, kind of shrink my picture into the small area of the features, but now I'm going to make it back to the original big picture and then give them some ideas about what they are. So one thing I can do is to do the unpooling. We know the pooling is to go from the big one into the small one, but now I can go from the small one in a reverse way to back to the big one. Okay. One thing I can do is to say, I simply expand each of this into 4 same value area. Okay. So instead of 2 by 2, I expand this into 4 by 4. Okay. Because in my original operation, I'm reducing that from 32 into, 22 into something. I keep getting it smaller and smaller, but now I'm going to try to go back to the original. Okay, so I can do this unpooling, or kind of from the original small one back into the big one. Okay. Another way to do this unpooling is not to say from 1 into 4 individual cells, but from 1 into one of them. Okay, so in the big one, only one of this cell here will keep the value. The rest of them, they're going to be 0. Okay, so both are ways for us to be expanding from a small picture into a big picture. Which way do you think is better? This one here, take this one and make it to be this one. It's like what? It's like when you have a low resolution picture and you simply expand that to be a big picture. Then every original picture becomes to be a block. Okay, so it will be still the same picture, but it's going to be very coarse, not so much details. Okay, but this will keep the overall shape because it's going to be very coarse. Okay, something which you're just expanding that into something which is not so visible. But this one here is going to keep your resolution, okay, to be this resolution, and you would have the details, but it's going to have a lot of empty ones in between. Okay, so for some of the pictures, okay, this one here actually would give you the kind of details that you want to see. Okay, you will be coarse. Okay, you won't be as coarse. You won't be as kind of bigger block, but you will have more details. Okay, so coming back to this picture, okay, so you can see that this one here is a pretty good picture, And if I expand it in this way, it still has all the detail because the resolution of the picture right now is still bigger than the screen itself, okay? But if I make it bigger and bigger, okay, you can see that, okay, sometimes that, okay, let's go to look at this. Okay, then when I'm in this one here, you can see that each of these pixels is no longer a pixel. So when I show you just part of this, you may not be able to see that this is actually a deer, right? Because it's kind of the perception for you to be able to capture the feature of this in such a coarse grain, okay, it's not as useful, okay? But if I have some pictures that is kind of like in this one here, okay, it will have enough detail, okay, and that would allow me to be able to say, even if I make this to be lighter, still I can capture that the overall shape of a deer. Okay, so in many ways that we'll prefer to be able to do this rather than this. Okay, because this actually will lose the detail. Okay, so one thing we can do is to try to kind of keep the idea. When I do the max pooling, I have the original pictures, right? And I know that for each of these 4 cells, the 2x2, I'm taking the largest value from one of the specific relative position in the 2x2. So when I try to do the upsampling, I take this value and put it only in that position where I used to take the max. Okay, so the relative position when I'm going down, taking the max pooling, I remember not just the value, but also remember which particular position is taken from this 2x2. So when I do the upsampling, I would just keep that position and use that value in that position only. The rest of them, I would fuse with 0. Okay, so you can see that roughly from our human perception, the relative of these significant points in here and in here are going to be the same. Okay, so in terms of features, okay, the overall shape will be kept. Okay, when I'm doing the downsampling and upsampling, okay, the relative position will be kept. Okay, so this is the way that people would prefer to do. Okay, when they are doing the upsampling, that when they try to use a convolution to capture the feature, but they also try to do the upsampling. But when they do the upsampling, after they have learned something, okay, they will keep the relative position, and so that they will be able to find the shape. Okay, so this is the strategy for us to be able to do the semantic segmentation. So semantic segmentation, we still do the convolution, okay, and we use the downsampling to do it this way, okay, but when we try to make the output of the segmentation, try to make the prediction, we try to come down and try to expand that. And when we expand that, okay, we can use the information from the original downsampling in order for us to do the upsampling, okay? And in that way, we will be able to find out what are the, kind of the individual pixels, what's class which is supposed to be there. Okay, so the semantic segmentation is still using the idea of the convolution. From the input, I try to capture the features, okay? From the features, then I will be able to identify what objects are in each specific area, okay, or in specific, kind of original picture. But rather than going through each of these convolution, going through minimal of the subpatch, I can take the whole thing, okay, and use the convolution strategy here to identify all features together. And then once I know that all features are in where, then I can try to reverse them to that each individual pixel know which particular class they belong to in the feature space. So in the feature space, I can expand it in this way. Then I will be able to label each individual pixel to say that you belong to certain class because you belong to that particular feature. And the upsampling strategy is simply to let you try to identify your relative position in the whole picture. And in that way, we'll be able to identify each individual pixel, what is the class it is about, okay? And in that way, we'll be able to show, okay, each of the pixel in the original picture, what class it belongs to. And in that way, we do the segmentation for each object. Okay, so the semantic segmentation simply say, here, when I have two cows, for each of these, I will simply say, oh, this belongs to a cow, this one belongs to a cow, so therefore, when I show the segmentation, it will show that both of them to be in the cow. Okay, so the two cows are actually shown as the same class, okay, because we are just trying to say that what is the each pixel belong to. If it belong to a cow, they will be shown as a cow. So therefore, any of the pixels in these two different cows will still be shown to be a cow, and they are actually shown together. Semantically, this is correct, okay, because each pixel, we can tell that whether it's a cow or it's a grass or it's a sky, okay? But of course that we don't do individual instance, and so sometimes this is not useful. And so we would like to be able to change it so that we actually can report to say that whether it is the first dog, where is the shape of the second dog, where is the shape of the cat. Okay, and this is called the instance segmentation. So to expand from the semantic segmentation into instance segmentation means we need to be able to identify each object in its own shape, okay? Which means that we need to be able to do the object detection to say that in this whole picture here, there's a dog. And this is the area that has a dog. And this one here also should be identified to say, oh, I found another dog. And this is the area for me to show that this is a dog. And this is the area which has a cat. So if I can identify each of this to say this is a dog and this is another dog, this is another cat, then I will be able to divide the semantic segmentation into instance segmentation to say this one here is different from that, even though both of them belong to a dog. Okay, so to do that, to do the instance segmentation, the first step is to do the object detection. And to do the object detection, basically, is to simply say that, okay, we're going to expand the original convolutional neural network, okay, the CNN. When I take the individual picture, okay, originally my individual picture would simply go through the CNN and then tell me which particular class has a high score. You would simply say, oh, here, this is a picture about a cat. Okay, so you have a cat with a high score. Okay, but in the CNN here, I can also try to train to say that in this picture here, okay, can you show me the bounding box, okay, which has something meaningful, okay? So the CNN here, instead of producing just the prediction to set what the cost, it should also show me the numbers. The numbers here identify the XY position, which is the corner, and then the height and weight. Okay, this whole thing here, including the cat in there, or the object in there. Okay, so CNN here, we know how to train that system so that you can produce the cost score, right? How do we do this? We define CNN, we give it the layers. Then we identify what? The loss function. The loss function here, I have a label for this, and this is the score, okay? Then from score, the loss, I can define the loss function. I use the loss function. I do the back propagation. So I train the network. And the network, next time when I give it the picture, you should try to have all of this weight change so you can give me a high score. Okay, that's the way we are doing this training for the classification. Now, suppose I change it. I say, here, this is a picture. I want you to show me the bounding box. So the output now from here is not going to be just one score, but it's going to be 4 numbers. The X, Y, and the WH. Okay, so this one here, going through the network, you should give me 4 numbers. Here, how many numbers do you get? How many numbers do you get? 1,000, because 1,000 scores. But here, I want to get 4 numbers. Okay, and from this picture, could I have what is going to be the desirable output in this picture here, given the original picture? The original picture, the label is cat. But the original picture here, if I want to do the bounding box, can you tell me where the bounding box is? As a human. So if I give you the picture and ask you as a human to say, okay, show me the bounding box of the cat. Can you do that? Of course. You can say, okay, I draw a box and here, this is my output. And this is what we call as human labeling, right? I give you a picture, I say, okay, draw the area which is the cat. You can do that. So actually, we have the ground truth of the bounding box X, Y, and HW. So I have the correct answer, and I have a CNN, and I have the current prediction. So can I train the network? This, don't think about this to be cat or something. Okay, I have a network, I have a picture. I ask you to train the network to produce 1,000 score. And the 1,000 score here, I have the correct label. So I compare with your prediction with the correct label, and I use that loss to train the network. And I hope that doing this over and over again, I will be able to have 1,000, which is going to be close to my prediction. My prediction should be close to my ground truth. Here, I have an input picture, I have a network, and the network here is supposed to produce 4 numbers. I know what is the correct 4 numbers, and here I have the network. You will make the prediction of the 4 numbers. Can I somehow train the network so that when I look at the picture, you will give me the 4 numbers that are correct or close to the correct answer? Yes or no? If I have a network which can produce 1,000 number, if I have a network, I want to produce 4 numbers, which is close to the correct answer, can I do it? If you trust AI, you should say yes. Because this is the input, this is the network. the output. The output is a prediction, and I have the ground truth. So giving me any kind of input with the ground truth, with my prediction, if I can define the loss function, I should be able to train the network so that you will, next time I give you the picture, you should be able to produce 4 correct numbers. Just like here, I ask you to produce 100, 1,000 correct numbers. Okay, so to do this mathematically or programming wise, is the same thing. Just one is producing 1,000 number and one is producing 4 numbers. And both of them, there are some ground truths. Okay, so we're just trying to train the network. If you have enough picture, then I will be able to say, next time when I see this one here, you'll give me 4 numbers and it will be close to the bounding box here. Okay, so from the CNN's point of view, these are 2 different tasks. Okay, one is classification. The other is what we call as localization, to find the location of the picture, of the object in the picture. They are exactly the same structure, okay? So there are actually 2 different tasks. One is to produce the numbers and we use the loss, soft loss to tell me what is the cat. The other one is train the network to find the bounding box, and the bounding box, I will compare that with the correct bounding box, and that will give me another loss function. So this one here is one training task, okay, with one loss function. This one here is another training task with one loss function, okay? And if I want to have both of them, I simply put them together. Mathematically, they are just, instead of 2 loss functions, I combine the loss function together, then I train the network. And I want my network here, my CNN here, to be able to have low loss here and here together. Okay, so this one here, actually, even though it, for our mind, it seems like, how can you do that? How can you find out the location? But if you trust AI, just give the task to AI. AI should be able to give you 4 good numbers, just like AI is able to give you 1,000 good numbers. Okay, the CNN architecture is the same. There is no difference. Just the training is different because your loss function now is changed from 1 to both of them together. You get it? Okay, so we now formulate the problem, object detection, okay, to be classification plus localization together, and then try to train the system to be able to work on both at the same time. Okay, and in terms of training, it takes more work, but in terms of the result, okay, you should be able to produce, multiple things, and each of them you will say, oh, there's a cat in some location, there's a dog in some location, there's a dog in some location. You should be able to produce all of this. With that, then we will be able to say, okay, yeah, there are multiple objects in there, and then for each of the objects, okay, then we will be able to see that what's going to be the specific location, okay, because we already talked about the segmentation. Is that if I give you this picture, you should be able to identify, okay, in terms of inside of this each pixel, whether it's a dog or not, okay, and so therefore for each of this bounding box, then I can do the segmentation, and you should be able to do the instance segmentation of the dog. The first dog, second dog, the third one, which is a cat. Okay, so coming back to this 4 task, the beginning. Okay, maybe we can just look at this one. Okay, so the first one, we now have already most familiar with, just like in your homework, just like all discussion of the neural network classification. I give you a picture, okay? And I give you some labels to say that, what they are supposed to be. Okay, feed that into the network, you produce your prediction. Compare the prediction with the label to see how different they are. Use the backpropagation, update your network so that next time when you see the picture, you give me the right prediction. Okay, classification. Okay, object detection. I give you a picture. Okay, you are supposed to tell me what object. Okay, and maybe you will do this multiple times, so you have multiple objects. Okay, then for each of the objects, I try to identify what is going to be the class in there. Okay, now to do this one here, if I give you one, okay, if I give you one, and I know that the correct answer is this is a cat, but now I train the network to say, I know there's a cat. Okay, give me the bounding box. And the bounding box is supposed to 4 numbers. The corner pixel and the height and width, 4 numbers. So from the neural network's point of view, just 4 numbers. And here I have the label, ground truth 4 number. Here I have the prediction 4 numbers. Okay, so I compare these 4 numbers. I have the loss function. I use that to train the network. I should be able to train my network so next time when I see this one, you produce the right 4 numbers. Instead of 1,000 numbers, just 4 numbers. And so therefore I can minimize my loss, and so I can find the loss. Okay, and so that's going to be the way for me to try to find the bounding box. Once I find the bounding box, I use the strategy for semantic segmentation to say that, okay, in this area here, okay, I'm going to try to look at them and find the features, and then I do the upsampling. When I do the upsampling, then I should be able to identify the area which belong to the dot. Okay, the specific, kind of shape of the dot. And the rest of them, I simply say they are not a dot. And if they are not a dot, I don't use different color, I just use the original color. Okay, and so therefore that the original color, the original pixel will not be changed. But the specific area for the dot, okay, is going to be identified. And you can see that in this output here, the tail is actually also identified. So therefore the tail is labeled semantic as this, okay? So the for computer vision, okay, using just one idea of the convolutional neural network, CNN, okay, I can change the layers, I can change the filters, I can change the architecture, okay, and I can identify different loss function, okay, and then I will be able to produce different output. And different output, okay, will able to tell me whether it's going to be a object or it's going to be a bounding box, okay, and then I can use the segmentation here to say that I'm going to use the downsampling here to find the feature. But once I find the feature, then I tell each individual pixel what are the, which feature or which particular object, okay, they are in. And that will give us the semantics, the segmentation, okay? And so in that way, we can do the semantic segmentation, or we can also do instance segmentation. Okay. I know that this is a leap of faith to trust that CNN is so powerful, but you have already seen that CNN can actually identify object classification, right? You know that given any kind of picture, just give it to CNN, and CNN can train to identify, say, oh, this is a cat, this is a dog, this is something, okay? But you can produce 1,000 numbers, you can produce 10,000 numbers, okay, to say that what it's about. So to produce the specific location, okay, of the car, we train the network, and you should be able to do that because the numbers just as numbers. Okay, well, there's no 1,000 number, it's 4 numbers, it's the same network. And then in terms of the segmentation, okay, we just need to know the strategy for us to do the downsampling to find the specific feature. Once we have identified the feature, then we put it back in the original picture to say that, oh, I know that you are part of the car. And so therefore, I'm going to show you to be part of the car. Okay, and so I have this upsampling here to expand your individual features. And that particular individual feature is part of the car. So therefore, you must be inside of the car. Once I have done that, then I will be able to show you the whole segmentation. Okay, so coming back to the this one here, basically, once we have talked about the CNN, once we talk about the base strategy of convolution, talk about base strategy of the architecture, you can continue to, think in this way. Okay, the question is, how much data do you have? How do you define the loss function? Okay, if you can define a good loss function for your data, if you have enough data, you should trust the network can be trained well. The same strategy will be used later when we discuss the large language model. Okay, the large language model is the same idea, is how do you actually find the most important capability for you to understand the original input. Okay, when we're talking about large language model, you will be understanding the individual sequence of, languages or sentences. But here we are trying to understand the relationship between the pixels in the image. So both of this, actually, we're going to be using AI to train, okay? You don't need to know how AI actually find out the answer, but just let AI train. And when the AI has enough data, you have a good architecture, you should be able to get a good result. Okay? Okay, so let's stop here today. Next time, I'll think about whether I would do a little bit of more on the computer vision, because there's some more I want to talk. So I may spend a little bit more time to talk about something about medical imaging. Okay, but then I would start to talk about the natural language processing. Okay. Okay, great. Thank you.